So these equations should look extremely similar. The only thing that changes is that now instead of translational or linear velocity, we use omega, right, alpha for acceleration because it's our angular acceleration, and we use theta for our displacement, right? That's angular displacement. So what should theta always be measured in? Yeah, radians. Yeah, rads. My favorite. And I love when people say rads per second. Okay, so theta has to be in radians. Sometimes in your problems you'll see them given to you in revolutions, right? We ran into that in our homework. You have to make sure that you can make that conversion between revolutions and radians, right? It's still how much of the circle we've covered, right, 3 revolutions, but it has to be in radians in order for our equation to work. Okay, same with our velocities here, our omegas. They can't be in RPMs, right? Sometimes we'll get it in RPMs, which is revolutions per minute. So we need to make the conversion always to be in radians per second. Okay, so we need radians, radians per second, and radians per second squared. Okay, questions here on these 3 equations? All right, we're just going to kind of jump in here and start practicing some. All right, so we have a couple different things given to us here. First of which are radius. What do we see about radius? In centimeters. Needs to be converted. So that means we're at 0.098 meters. Rotational speed. What variable does that mean we're looking at here? Right. Yeah, our initial velocity, because it's going to come to a stop. Okay. So initial is 14. That means alpha is, what do we need to add to that 2.4? A negative. Good. Do you understand why we're adding that negative? Right, we're moving in the positive direction and slowing down, so it's be negative 2.4. And that means our final angular velocity should be 0. So we want to know how far did it roll before coming to a stop. We want to basically find out the distance it traveled. So there's a couple different ways we can go about doing this. Okay, the first of which would be to solve for theta, right? How many radians did it spin through? And then we can use the radius of that circle to help determine the distance it traveled, right? That's the easiest way to do it. The second way would be to find the circumference of it and go about it that way, but that's a little more complicated than we need to be. So first thing we'll do is solve for theta, right? We want to find out how many revolutions did it spin through before it came to a stop. So which of our kinematics equations could we use here? Has to be the third one because we don't have time. Okay, so it tells us it went through 40.83 radians. So what we could do is we could convert to revolutions and then find the circumference of the circle and then look at it based on that. But we have an equation that does it for us, right? We have an equation that says L equals theta times R, right? And L is the distance traveled. So we can just use that equation, right? L is the length of our the outer part of our circle, right? So that means if it travels that many lengths or travels that many meters, that's the same amount of distance that it would roll, right? So this was one of the first equations we got. So we know that our radians is 40.83, our radius is 0.098. Which means it traveled a distance of about 4 meters. We want to find the angular acceleration here and what's the angle through which the drill has rotated. So there's 2 parts to our question on this one. Okay, this question asks us for 2 different things, and it also tells us initial velocity is 0, time is 3.2, and then what is this value here? What variable? Yeah, our final velocity. So we need to convert that to radians per second. So if you want to do your T-chart, it would look something like this. Revolutions per minute, right? And we know that 1 revolution is 2 pi radians, and we know 1 minute is 60 seconds. Right? We could have also used that shortcut that we developed last class, times 0.105 or times 0.1047, depending on how exact you want to be. Not a huge deal, right? It gives us a little bit of a different answer, but not anything concerning, right? So either of those would work fine. If you use the shortcut or if you use the regular conversion method, it's fine. Not a big deal. Okay, this gives us our final angular velocity. So 2628.5. Okay, so to solve for alpha, what equation could we use? Yeah, the first kinematics, right? Sorry, thank you. That would change my math then. So 821. Okay. Okay, then if we want to find what angle the drill's rotated through, that means we're solving for what variable? Right, we're solving for theta. Okay, any kinematics equation would work here. However, it's not at constant velocity, so we could not do this equation. Right, that won't work because it's not at constant velocity. It's speeding up throughout this process, so you have to use one of your actual kinematics equations. This only works if you're at constant angular velocity. Okay, so you have to use one of your kinematics. Any of the three would work. Okay, so if we wanted to find out how many revolutions the drill has made, how do we go from radians to revolutions? Divide by 2 pi. 2 pi radians is equal to 1 revolution. Okay, so this would be a question that you'd get a lot. It wouldn't say anything about the angle. It would say how many revolutions has it spun through, right? And you have to know, that means you solve for radians first, and then you convert to revolutions. So as we convert to revolutions, make sure you divide by 2, divide by pi, or divide by parentheses 2 pi, right? Otherwise, it won't come out right. So it rotates through about 669 or 670 revolutions. Okay, you could have also converted that radians to degrees if you needed to do that, right? 2 pi radians is 360 degrees. Is that not what you got? Well, I almost put 70, but I changed it to a 6. 669.
Wait, so how would you get to like a degree?
So if I wanted to go to degrees, I'd go okay, let me find some room here. I would go 4205.6 radians, and I know that 2 pi radians is 360 degrees. Right, so I'd multiply by 360 and divide by 2 pi.
Same as 180 over pi.
Exactly, yeah, that would work too.
And is that what you would play if it asks for the angle, or you can leave it in radians?
If it's just the angle specifically, you can leave it in radians. Yeah. Because a radians is still a measurement of the angle, right? We just think of degrees more often. Okay. Was something wrong?
So the angle through which it goes means revolution?
Could be in radians. No, I just made it one extra step to go to revolutions.
Oh.
Could leave it in radians there.
Oh.
But in most questions, that won't be the way it'll be worded. It would say, how many revolutions has it gone through? In which case, you would have to end up converting to revolutions. Okay? Okay, so try this one on your own, because this one does that. How many revolutions does the machine go? Okay, so it starts from rest and accelerates to 5 revolutions per second. After this, the machine is unplugged and comes to a stop in 12 seconds. So this has 2 distinct parts to it. Okay, so it starts from rest and accelerates to 5 revolutions per second, which you'll need to do a conversion there in 8 seconds. After this, the machine is unplugged and comes to a stop in 12 seconds. Through how many total revolutions does the machine go? You have to make sure that you solve these completely separately, and then you'll add your number of revolutions together. Because during this time, this 20 seconds, there's not a constant acceleration, right? They're speeding up and then they're slowing down, which means you have to do 2 separate kinematics equations to help you solve for these. Okay?